Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will see how to design the differential amplifier or a subtractor circuit using the op-amp. Now we already know that this op-amp is differential amplifier which amplifies the difference between the inverting and the non-inverting terminal. But whenever this op-amp is used in the open loop configuration, then the gain of this op-amp is quite high, and because of that your output will always be get saturated. And to avoid that, we always need to use this op-amp in a feedback circuit. So then we had seen this inverting and the non-inverting op-amp configuration where we have applied the input either to the non-inverting or the inverting input terminal. So now let us see how by combining the inverting and the non-inverting op-amp configuration we can design the differential amplifier. So by using this configuration we can use this op-amp as a differential amplifier in a true sense, because here we can control the gain of the op-amp by controlling the value of this resistor R2 and R1. So let us see how this configuration will act as a differential amplifier. So now if you closely look this configuration, it is the combination of inverting and the non-inverting configuration. So if you consider this voltage source V1 alone and consider this voltage source V2 as 0, then it will be the inverting configuration. Similarly, if you consider only this voltage source V2 and if you consider this voltage source V1 as 0, then it will be the non-inverting configuration. So this configuration is the combination of inverting and the non-inverting configuration. So to get the final output, we need to use the superposition theorem. So what we will do, we will consider only one voltage source at a time and we will consider the remaining voltage source as a 0. So first we will consider this voltage source V2 as 0 and we will assume that this voltage source V1 is acting alone. So let us say in this configuration the output voltage is VO1. So this output voltage VO1 can be given as minus R2 divided by R1 times this voltage V1, as it is the inverting configuration, right? Similarly, let us say if voltage V1 is 0 and let us say this voltage V2 is acting alone, then in that case our output voltage, let's say VO2 will be equal to 1 plus R2 divided by R1 times this voltage source V2. So now if we consider this voltage source V1 and V2 acting simultaneously, then our output voltage Vout will be equal to VO1 plus VO2, that is equal to minus R2 divided by R1 times this voltage V1 plus 1 plus R2 divided by R1 times this voltage source V2. So now if you observe here, the gain that is applied to both the input is different, and suppose if you want this output voltage Vout as K times the difference between the two voltages, let's say that is equal to V2 minus V1, then we need to ensure that the gain that is applied to both the input is equal. So suppose in this case, if the gain that is applied to both the input is, let's say that is equal to R2 divided by R1, then in a true sense we can use this configuration as a differential amplifier where the output will be the difference between the two input voltages multiplied by the sum gain factor K. So now let us see how we can achieve this equal gain. So here in this second term, instead of this 1 plus R2 divided by R1, we required the term that is equal to R2 divided by R1. So somehow we need to arrange this term in such a way that we can get this term R2 divided by R1. So now we can write this term 1 plus R2 divided by R1 as R1 plus R2 divided by R1. And if we want this term R2 divided by R1, then we need to multiply this term by the factor of R2 divided by R1 plus R2. So here to get this term, what we can do, instead of applying this voltage source V2 directly, we can apply this voltage source V2 by using the voltage divider. So let us see how we can achieve this term R2 divided by R1. So here what we have done now, we have applied this voltage source V2 using this voltage divider circuit. So now if you see at this point, then at this point let us say the voltage is V plus. So this voltage V plus will be equal to R2 divided by R1 plus R2 times this voltage V2, right? So our voltage V plus will be equal to this term. Now we know that the output voltage Vout because of this voltage source V2 will be equal to 1 plus R2 divided by R1 times this voltage V plus. So now if we put this value of V plus, then we will get 1 plus R2 divided by R1 times R2 divided by R1 plus R2 times this voltage V2. So if we simplify it, then we will get the term R2 divided by R1 times this voltage V2. So now if you see, if we consider this voltage source V1 and V2 simultaneously, then our output V out will be equal to minus R2 divided by R1 times this voltage V1 plus R2 divided by R1 times this voltage source V2, or we can say that our output voltage will be equal to R2 divided by R1 times the difference between the voltage source V2 and V1. So now if you see this configuration, here the output voltage is the difference between the two input voltage multiplied by the factor of R2 divided by R1. So in this way, using this configuration, in a true sense, we can use this op amp as a differential amplifier. So now let us see where this differential amplifier can be used. So apart from performing the mathematical operations, this differential amplifier can also be used along with the sensors. So let us say here we have a RTD and it is connected in a balance bridge circuit, and the output of the two arms of this balance bridge is connected as an input to the two ends of the differential amplifier. So here initially this bridge is balanced, but as the temperature changes, the value of this resistance R will change, and because of that the voltage that appears at the two input will also change. So when the bridge is balanced, then the input at the both ends of this differential amplifier will be equal, that is V1 equal to V2. But as the temperature changes, the value of this resistance R will change, and because of that the voltage that appears at this end will also change, and we can amplify the difference between the V1 and V2, and we can use this output to control the another circuitry. So let us say if we want to control the temperature of some room, then we can use this sensor along with this differential amplifier. So by triggering the another circuitry based on this output voltage, we can control the temperature of the room. So this is how this differential amplifier can be used along with the sensors. Now here the problem with this differential amplifier is that the input impedance of this differential amplifier is very low, and it depends upon the value of this R1 and the R2. So if you see in this configuration, the input impedance that is seen through this end will be equal to R1, while at this end if you see, the input impedance is equal to R1 plus R2. Or in general term, let's say if you are applying the input voltage between the two ends, then in this case the input impedance Zin will be equal to 2 times R1. So as you can see here, the input impedance of this differential amplifier is very low, and because of that it is quite possible that your source might get loaded. So one way we can avoid this by using the buffers before the input voltages. So as you can see here, before applying this voltage V1, suppose if we use the buffer, then the input impedance of this buffer is very high, and in this way we can avoid the loading of this source voltages. But in most of the practical cases where you are dealing with the very small input voltages which is coming from the sensors, in such cases instead of this differential amplifier, the instrumentation amplifier is used, and we will talk more about this instrumentation amplifier in a separate video. So this instrumentation amplifier is a very high gain differential amplifier, and the main advantage of this instrumentation amplifier is that it is having a very high input impedance. So that is particularly useful when we are dealing with the sensors. But in general applications, we can use this differential amplifier along with this buffers. So that is being said, now let us see some examples based on this differential amplifier. So here we have one differential amplifier, and we need to find the output voltage of this differential amplifier. And here assume that the biasing voltages which is being applied to this op amp is plus 15 and minus 15 volt. So here to find the output voltage, what we will do, we will consider one voltage source at a time. So first let us assume that this 2 volt voltage source is acting alone. So if we consider this 2 volt voltage source acting alone, then in that case let us say output voltage is VO1, and that will be equal to minus 5 divided by 1 times this 2 volt, and that will come out as a minus 10 volt. Similarly, if we assume that this 3 volt voltage source is acting alone and this 2 volt voltage source is equal to 0, then in that case our output voltage, let's say VO2, will be equal to 1 plus 5 divided by 1 times this voltage V plus, and here this voltage V plus is equal to 8 divided by 8 plus 1 times this input voltage, that is equal to 3 volt. So our output voltage VO2 will be equal to 16 volt. So now if we combine these two input voltages and assume that these two input voltages are acting simultaneously, then in that case our output voltage Vout will be equal to VO1 plus VO2. So our output voltage will be equal to 16 minus 10, that is equal to 6 volt. So this is very simple and the basic example based on this differential amplifier. Now here you also need to consider the biasing voltage that is being applied to the differential amplifier. So let us take one more example and we will see how this biasing voltage can affect your output. So if you see this example, this is very similar to the previous example, but here in this case let us assume that our bias voltage is plus 12 volt and minus 12 volt, and we want to find the output voltage. So here once again what we will do, we will assume only one voltage source is acting at a time and we will find the output voltage, and then we will combine the individual responses. So let us say output voltage VO1 is the output voltage when this 2 volt voltage source is acting alone. So our output voltage will be equal to minus 5 divided by 1 times this 2 volt voltage source. So that will come out again as a minus 10 volt. And now let us assume this 5 volt voltage source is acting alone. So in that case our output voltage VO2 will be equal to 1 plus this 5 divided by 1 times this voltage V plus, that will be equal to 6 times V plus. Now this voltage V plus will be equal to voltage divider that is applied at this point. So it will be equal to 4 divided by 4 plus 1 times this 5 volt input voltage, and it will come out as a 24 volt. So our output voltage VO2 will be equal to 24 volt. So now in this case if you see, our total output voltage Vout will be equal to VO1 plus VO2, and if you see it will come out as a 24 minus 10, that is equal to 14 volt. But in this example we have applied the plus minus 12 volt. So our output voltage cannot go beyond this plus minus 12 volt, right? So our output voltage will be get saturated at the 12 volt. So apart from the input voltages, you also need to consider the biasing voltages which is being applied to this op-amp. So that is being said, now let us see the third example, and this example is for your exercise. So here instead of single input voltages, we have applied the multiple input voltages at the inverting and the non-inverting terminal, and we need to find the output voltage of this configuration. And here once again assume that the biasing voltages for this circuit is plus 15 and minus 15 volt. So try to solve this example by yourself and do let me know your answer in the comment section below. So I hope in this video you understood how to use the op-amp as a differential amplifier or as a subtractor. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.